Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to tell you about Grothendieck's version of cohomology, as opposed to the version of cohomology that I've set up so far, which is via check cohomology. Grothendieck's version is rather nice because his cohomology is intimately related to the X functor, and hence is useful for looking at splitting theorems. And in fact, one of the things that I want to show you in this video is how he proved his splitting theorem for sheaves on coherent sheaves on P1. Okay, so let's look at Grothendieck's theorem. I won't go through the details of how he set it up. It's quite a big theorem and requires a fair bit of machinery, but it's easy to state the result of what he has here. Okay, so if you have any quasi-projective variety X, then you look at this category, quasi-coherent X, okay, it's an abelian category, and in fact it has enough injectives. So you can always form injective resolutions of quasi-coherent sheaves. And as a result, you can talk about derived functors. Okay, so we have this global section functor H0. This is a left exact functor, because remember this is the same as just homomorphisms from O to something, so it also follows from left exactness of the hom functor, and so you can talk about its derived functors. And in fact, more generally, you can look at the derived functors of hom, and that gives you X. Okay, so in particular, that's going to give us a way to look at cohomology. His definition of cohomology is as this derived functor, HIXM, is going to be defined just to be essentially xi of OX into M. So remember, H0 is just homomorphisms, where I equals 0, case here, of OX into the quasi-coherent sheaf here. So its derived functors x to I give you the derived functors here. Okay, so in other words, you basically take an injective resolution of this M. Okay, you apply H0 to this injective resolution, and the cohomology, the ith cohomology of that will give you the ith cohomology of this quasi-coherent sheaf. Okay, so maybe you're not too familiar with this, but for this video, I just want you to know a little bit about the case where I equals 1 and also about Yoneda X, okay? And so we'll just look at what it means for I equals 1 here, H1 XM. What does that mean, okay? So firstly, if you have M and N are quasi-coherent sheaves, Yoneda X, we can give an alternate definition of this X1 of M to N. What is that? The XT stands for extensions, and in fact these are essentially just extensions of M by N. Okay, so this is the set of isomorphism classes of short exact sequences E, like you see here. Okay, so firstly, what is it? So firstly, you'll have a sub sheaf N here, and a quotient sheaf M, and the E goes in the middle. Okay, so these swap around, so the N is here and the M is here, and it's just a short exact sequence like that. And of course, there are lots of short exact sequences. You can just change names of what's in the middle here. So we're going to look at isomorphism classes of this. Okay, isomorphism classes of this. So suppose you're given another one, E prime, this blue one here, 0 to N to E prime to M to 0. Okay, here's a short exact sequence. What's an isomorphism? So basically, it's a commutative diagram like this, where you have identities on the N and the M, and a morphism from E to E prime here, and once you have this morphism, the 5 lemma will tell you that this is actually an isomorphism. Okay, so that's an isomorphism. So we look at isomorphism classes of these. Now this is actually going to be a vector space over the ground field. Okay, so you can talk about addition in here. I won't go through how addition is defined. The only thing I want to tell you about this vector space structure here is the distinguished element 0 here. So what is the 0 inside here? That corresponds to a particular short exact sequence, and what is that one? Okay, as the name suggests, this is going to be the split short exact sequence. Okay, so N maps to the direct sum of N and M, maps to M, and the maps here, the natural ones. So N injects into this first summand here, and it goes to 0 here. And then the projection here is it sends all of this N to 0, and it's the identity on this M component. So that's the 0 element. So I guess all I want to say here is that this H1, okay, what you need to know for this video is just that this H1, you can think of just as the extensions from OX to M, and such extensions are basically just short exact sequences, okay, and the 0 element here is just the one that's split. That's all we need to know, okay, if you don't know your homological algebra so well. So what's Grothendieck's splitting theorem says? So this is really wonderful theorem because it tells you that you really know everything there is to know about coherent sheaves on P1. Okay, so for most projective varieties, okay, it's very hard to understand completely the category of coherent sheaves on it, but in this case here, it's completely worked out. Okay, so we'll look at the sort of the harder case, which is the torsion-free case. So suppose F is also torsion-free. Well, in this case, F is going to be a direct sum of very simple coherent sheaves that we already understand. So these are the line bundles OMI. Okay, so all the line bundles have this form OMI, and in fact, this will actually prove that all the line bundles have to have this form. Okay, so so it's going to be OMI, where Mi are some integers, and of course the number of summons. Well, this will give you the rank of this coherent sheaf. So the number of summons is just the rank. Okay, so this is the version that I want to show you the proof for right now. And so let's go ahead and prove this. And the way we'll prove this is we'll just use the identification of this cohomology with what we've seen using the check cohomology. The check cohomology is quite easily computable, and so we've proved several theorems about it, including Serre's theorem. So the first thing is that what I want to do to try to show this is, well, you've got to find one of the summons, okay? You've got to find one of the summons in here, and these are both, the summons of course here are both quotients and subsheaves. So actually what we'll do is rule for subsheaf first. Okay, so the first thing is that Serre's theorem tells you that there is a surjection from some direct sum of copies of some OMR onto F. So in particular, there is some map from some OMR into F. MR is some integer. And since this is torsion-free, okay, if this has a kernel which is non-zero, the image has to be, since it's an invertible sheaf, okay, if you look locally on any patch, you will see that this will have to be torsion inside here. So it has to actually be injective. Once you have a non-zero map from an invertible sheaf to here, okay, either it's going to be injective like this, or if it has a kernel, the kernel will also be full rank, so you get something that's torsion in the image. Okay, so there's an injection like that. Okay, so that's a good start. We can try to pick up one summoned. Okay, so that's good. So what we're going to do is we'll pick up that some summoned. Okay, so we'll inject this OMR into F, and we'll form a short exact sequence like this one here. Okay, so there's F, and the quotient of F by the image of this OMR I'll denote by F prime here. That's great. Now, unfortunately, it won't in general be the case that this will split. But what you can do is you can assume, you can look at all such injections, okay, and look at the one where MR is maximal. Okay, so that's going to be absolutely key here. Okay, we'll look at the one where MR is maximal, and then study that short exact sequence. Now, of course, to make sense of this, you have to realize that there is one where this MR is as big as it can be. Okay, why isn't it that you can't just get bigger and bigger MRs in here? And the easiest way to see this is to have some sort of bound on this. Okay, so how do you bound this? Well, let's just look at the global section. So remember, any global sections of this subsheaf will give you a global section of here. Okay, and this is an injective map. Okay, global section is the left exact functor. Okay, but it's also quite easy to see directly that if you have a global section of this subsheaf, it's going to give you that non-zero. It gives you a non-zero global section here. Okay, so what happens in this case? So you've got these global sections. So the thing that we know is Serre finiteness tells you that the dimensions of the global sections of this F, this being a coherent sheaf, is finite. Okay, so that gives you some sort of a bound because the dimensions of these, okay, the global sections of these is also finite, but it goes up with MR. Okay, it's the dimension of the global sections of this is MR plus 1. So if you pick MR to be too big, okay, then there's no way that this can inject into here. So such an MR maximal does actually exist. Okay, so what can we do? We have to use this maximality quite a bit to make this proof work, okay, and it's rather nice. So what's the first thing, okay? So the first thing that it means is that actually F prime is going to be torsion-free itself. So the quotient is also torsion-free. So why is that? So if not, it turns out that you can look at the torsion inside here and look at the inverse image of the torsion, okay? So the inverse image of the torsion includes the inverse image of 0, which is the image of this OMR. but it includes some extra stuff as well, okay, if the torsion is non-zero. And it turns out that what that will mean is that you'll get something bigger than this OMR, so it means that you can get a bigger MR there. Okay, so this is something I don't want to prove right here. Okay, it requires a little bit of thought, but it's basically a local sort of a calculation, and I want to show you more where these ideas here come into the proof. Okay, but that's not too difficult. Once this is torsion-free, what that means is that you can use induction because this is lower rank. Okay, the rank of this F prime, you've removed this from here, so that means it has rank only R minus 1. So it's the direct sum by induction of R minus 1 invertible sheaves of the form OMI, like that. Okay. So the most important part of this claim, and here we want to use maximality of MR once more, is that you've got this MR, okay, and you've got these from F prime, you've got these integers M1 up to MR minus 1. And I want to say this MR is going to be at least as big as all those previous M's. Okay, so that's the claim. And to do that, what we're going to do is we're going to use a certain long exact sequence that I've written here. I'm going to look at homomorphisms of, instead of MR, OMR here, OMR plus 1 into this short exact sequence. So look at homomorphisms of this OMR plus 1 into this F, this OMR plus 1 into this F prime, and then we use the connecting homomorphism, and we'll go up to the x1 of OMR plus 1 into this OMR. Okay, so that's what we're going to use, and this is going to be critical. Okay, so let's just have a look at this x here that we have written down. So the first thing is that, and this is something that's very important, is that remember invertible sheaves gives you, by tensoring, an autoequivalence of the category. Okay, and autoequivalences, what that will do is it's going to preserve short exact sequences like this, and also isomorphisms. Okay, all these sort of things go across. So of course, if you apply this autoequivalence, it doesn't change the x. You get an isomorphic X group. Okay, so that's the key thing. So what I can do is I can tensor this with the inverse of this OMR plus 1 to both of these and get an isomorphic X group or X space. Okay, so this becomes O. I've inverted that one. And this one here, so that's basically tensoring with O minus MR minus 1, means that this one goes to O minus 1. So this X group is isomorphic to X1 O into O minus 1. Okay, so this is a very important point. And this X1, remember what I said, is just of O into something, is just the global sections. So you're just looking at the global sections of O minus 1. But this is something that we computed earlier in this playlist as using check cohomology, and it's 0. Okay, so this is 0 here. Okay. So this being 0, what does that mean? So you have a long exact sequence here, but you get a 0 term here, so it means that this map here is surjective. So this implies it's surjective here. Okay, so you have a surjective map from here to here. Now what about this term here? Let's suppose we're in the case where this is false. So one of these is bigger than MR plus 1. So it's at least as big as MR plus 1. So since one of these summons is an O, OM, where that M is bigger, at least as big as this is not 0. So if you want to know why, if you want to know what are the homomorphs of OM to ON, okay, so the way to work that out is that you can apply this autoequivalence of the categories and tensor by O minus M. That'll get you O here and an O n minus M there, and since you're homing O into something, that's just global sections. Okay, and the global sections of O n minus M, this is non-zero precisely when n is at least as big as when this n minus m is non-negative. Okay, so if you get O, you get 1. So it's basically the dimension of this is 1 plus this integer n minus m. Okay, so this is actually non-zero because you're assuming that this is false. Okay, we're going to assume if this is not the case, else we're assuming this is false. So one of the summands here has something which the integer here is at least as big as this mr plus 1. So this is non-zero and this is surjective. That implies that this is non-zero. And since this is non-zero, you've got a homomorphism from a bigger value, an integer bigger than mr plus 1 in fact, into here. Okay, and that contradicts the maximality of mr. So it contradicts the maximality of mr, and that means that the else assumption that this is false must indeed itself be false. And we've chosen that this mr, this number here, is in fact at least as big as all the previous m's. The claim is proved. Okay, so let's see now how we can complete the proof of Grothendieck's splitting theorem in this torsion-free case. So that's rather nice. Okay, so I claim that, and this is the key point, when you get to this stage here, you look pretty close, right? Okay, you've written f as a short exact sequence where one of the terms is a big direct sum of these OMs, and then the corresponding kernel of that map is an OM, and you just need to show that this splits. So I claim that this splits. So let's see why this splits. Okay, so this splits. Why is that? Well, this is a short exact sequence, so it's an element of a certain X group. So the X group is this F prime, which by induction is this direct sum from I equals 1 up to R minus 1 of these OMIs to this OMR. And let's again compute this, and we'll use the same trick as we did before, okay? We're going to use the fact that, well, firstly, we can pull out the direct sum. Let's pull out the direct sum. And then secondly, we can apply this autoequivalence of tensoring with the invertible sheaf O minus mi to cancel this, to get you an O here, and you subtract mi from here. And then x of O into something, that's x1 of O into something is just h1. So it's the direct sum of h1 of this OMR minus mi. And the thing is that if you look at mr minus mi, we said that mr is at least as big as all of these. So these are all non-negative integers. And we calculated using check cohomology that these h1s of these O of non-negative integers, they're all 0. So this x space is 0, so that element, the corresponding element, this short exact sequence, it's an element of this x space which is 0, and the only 0 element that you have here is the split one. So this actually splits. And that tells you that, well then, since this splits, you have that this f is indeed isomorphic to the direct sum of this direct sum here with this one here. And that proves Grothendieck's splitting theorem, or at least the case where this is torsion-free. Okay. So there's a more general version of this theorem. So let me tell you the most general version, which really gives you complete information about coherent sheaves on P1. Okay? And it's shown by a fairly similar argument, so I don't want to repeat it here. I'll just tell you what the main ingredient is here. Okay? So similarly, you can show that if M is any coherent sheaf, okay, what can you do here? So what you can do is that if it's a coherent sheaf, well, in general, it may have a torsion subsheaf. This script T be the torsion subsheaf. So if that's the torsion subsheaf, we get an short exact sequence. 0 goes to the torsion subsheaf, goes to M, goes to the corresponding quotient. And since the torsion subsheaf has all the torsion in there, the quotient will be torsion-free. Okay, so the quotient is torsion-free. So by this version of the Grothendieck splitting theorem, you know it's a direct sum of these line bundles or invertible sheaves of this form. Okay, so that's something that you have there. And the point is that now you can show that this splits. So that tells you that M is isomorphic to what? It's isomorphic to, firstly, this torsion-free, so it's an isomorphic to this direct sum of invertible sheaves, and its torsion part. So that's the more general theorem. And analyzing the torsion part is quite easy because you can do this just locally on patches because it's supported on a finite set of points, this torsion subsheaf. So how do you prove that? So as usual, the proof is quite simple. All you have to do is to look at this element inside the corresponding x space, and the x space will be x1 from m mod t to this t. Now this m mod t is just like this, and since these are just is direct sum of invertible sheaves, you can pull the direct sum out and you can use this trick of just tensoring with the inverse invertible sheaf. So at the end of the day, what you'll do is you look at H1s again, but what H1s will be, well, you're just tensoring torsion sheaves by some inverse of some invertible sheaf like that. But that's just a torsion sheaf. So what you need to do is you need to look in the X space, which is now just a direct sum of H1s of torsion sheaves. And the key point here is that H1 of a torsion sheaf, as we've seen here, a torsion sheaf on any curve, in fact, is going to be 0. So this splits. And in fact, this argument, it requires a little bit more work if you don't have Grothendieck splitting theorem here. This argument actually works for any smooth curve x. You can show that the torsion part splits off. But to do that part of the calculation, you need a little bit more machinery, okay? And probably the easiest way to do that is to use the local global x spectral sequence to show that if you only know that this is torsion-free, okay, why is it that the x1s, okay, are going to vanish? You can compute that as h1 of this torsion sheaf. Okay, so in this video we've shown that this wonderful Grothendieck splitting theorem, that any torsion-free sheaf on P1, which is coherent, is just a direct sum of invertible sheaves, so things of this form, okay? And the way it uses beautifully the theory of cohomology, okay? The fact that cohomology, H1, the key thing is that H1 gives you a lot of extension groups, okay? And if you can show a lot of these are 0, that means things split. I hope you enjoyed this adventure in pure mathematics.